We would now like to study the properties of what happens when we put a current loop in a magnetic field. So for simplicity, the current loop that I'm going to look at will be just some type of wire. So we have a current I on all of these legs, and that's our current loop. And what I'd like to ask now is what happens when we put this current loop in a magnetic field. And for simplicity, let's just indicate our magnetic field B, pointing like that. And now, when we begin to make the analysis, we've already studied the example that we're going to look at is B is uniform. And when we know that we put a uniform current loop in a current loop in a uniform magnetic field, then the force on that loop is the integral of I ds cross B. But because B is uniform, I can pull that out of the integral, cross B. And the integral of ds around a closed path is 0. And so the force on a current loop in a uniform magnetic field is 0. But what about torque? Now, we want to consider torque on the loop. And because the force is 0, we can choose any point we want in which to calculate torque. So if the force on the loop is 0, it doesn't matter what point we calculate torque about, we'll get the same answer. So let's draw our loop here. And we have a current I. And we have a uniform field B pointing this way. So we have a current going around the loop. And what we have to calculate is the force on each leg of the loop, which is definitely non-zero. Remember, a force on a leg of a loop is the current I ds through that leg cross the magnetic field. So when we look at that, if we label this leg 1, 2, 3, and 4, we see that this force on legs 2, I is in the direction of B, and remember, the ds is always in the direction of the I. And let's just make sure that we can see this. So we have leg 2 here. We have the current I, and the ds is pointing in the direction of I. Here, our I is pointing in the opposite direction. And our ds, if we calculate ds going around this loop, the ds is that way. And in both of these legs, the force is 0 because the ds is parallel to B. So the force on legs 2 and the force on leg 4 are 0. Now, in leg 2 and leg 4, we do have forces because we have the ds going this way and a ds, say, going down that way in the direction of the current. And so what we want to do is calculate the forces on those two legs. Now, let's think about that calculation. So the force on leg 1 is equal to I ds1 cross B. And when we make a calculation like this, let's just choose a set of unit vectors to make things a little bit easier. That's our little df. And we get I. Now here we're going in the j direction, dy j hat cross B I hat. And when I take j hat cross I hat, remember I hat cross j hat is k hat. So j hat cross I hat is minus k hat. We get minus I dy b k hat for the df1. And when I integrate that around the loop, around this leg, let's put some dimensions in here. We'll call this a width w, and here a length d. So I'm just integrating along this length. So it's just the integral of dy is minus I wb k hat. So on this leg, we have a force that's in the minus k hat direction. So we have that force F1. Now, without repeating this whole calculation, the force on leg 3, well, leg 3, the only thing that changed was the direction of ds. And on leg 3, ds is pointing down, so we'll get a change in sign. So we get I, W, B, K hat. And that's a force on leg 3 coming out of the plane of the figure. When you add these two things together, you get 0, 0, corresponding to the idea that there's no force on this loop. But torque is a little more complicated, because when we talk about torque in general for any particular leg, it's the integral of some vector from some point to that leg times a little df on that leg. And then we're going to add this up over the legs. So now we want to calculate this torque, and what's important is to have a good coordinate system. So I'm going to start again and think a little bit about choosing a smart coordinate system. Well, on this leg, the force we saw was into the plane of the figure. And over here, the force was out of the plane of the figure. We had I hat, J hat, K hat coming out. We had a current I in this loop. And I'm going to choose a point P here to look at the force. Now, in general, torque is some RP across the leg. And I'll do this calculation first a bit simply. I'll just assume that the whole force is acting at P. And that's why I chose P in the middle of the leg. Then the torque total about P is the torque on leg, we call this leg 1, remember? Leg 1, about P of leg 1, plus the torque of P about leg 3. And this one, when we put all the force acting at that place, is 0. But if you think about it, if the force is always going into the plane of the figure, then the r vector for a point down here is exactly canceling the r vector for a point up there, and so torques will cancel in pairs, so the idea that the torque on that leg is 0 makes sense. Now, for leg 2, let's once again just say that the whole force, which is coming out of the plane of the figure, F3, is acting here. And our vector from RP to this point 3 is there. So what we have is simply the vector RP3 cross F3. And let's write that out. R3, we had a distance that this was length D, and this was W. And so we have D I hat cross F3 was I, W, B, K hat. And I hat cross K hat is minus J hat. So we get I times W times D times B in the minus J hat direction. And that is the total torque. As an exercise, you can calculate what would happen if you just took a little element and integrated from one side to the other to get the torque on all of these little pieces. You'll get the same result. Now, let's think about our loop again. And this is where the magnetic dipole comes in. Our loop has a current like this. We had I hat, J hat, and K hat. And our magnetic moment, by the right-hand rule, as you look at this loop, N hat, right-hand rule, is into the page of the figure. So our magnetic moment, mu, remember, it's in the direction is perpendicular to the plane of this. It's the current times the area, which is WD. Now the direction into the plane of the figure here is minus K hat. So that's our magnetic moment associated with this current loop. And now, when we want to calculate the total torque, we want to look at it in terms of our magnetic moment. So what we want to define a definition of torque on a current loop in a uniform magnetic field is mu cross B. Now let's see if it corresponds with our calculation. For our current loop here, we have the dipole moment pointing in the minus k hat direction. Our magnetic field is pointing in the I hat direction. So the B field was going in the I hat direction. And k hat cross I hat is negative j hat. And so we get I omega d B in the negative j hat direction. And that's exactly what we calculated. So this is the torque on a current loop in a uniform magnetic field, and we refer to it as a torque on a magnetic dipole in a uniform magnetic field. So here for this calculation, B was uniform, and that's how we made this calculation. So that's our first calculation about torques on a dipole. Now let's look at an example of force and torque on a dipole. Let's take a current loop here, and let's consider a point, a height z above it. And the current loop, by Biot-Savart law, produces a magnetic field B up here at a height z. And for the moment, we're going to just talk about B as having a z component, which is a function of z in the k hat direction. And now let's put a dipole, and for the moment let's fix the dipole mu so that dipole moment has a z component also in the k hat direction. And what we'd like to do is look at the force on that dipole, which we refer to as the gradient of the dipole moment dot B. Well, mu dot B is simply mu z bz here at this point. And in general, so we have the gradient. Now, in general, the gradient has three terms, so we have to be a little bit careful. There's a d by dx of mu z bz plus d by dy of mu z bz plus d by dz of mu z bz. Now, in this case, because this is in the z direction, you might say, is there some type of gradient, some partial derivative of the z component in the x direction? Now, technically, the magnetic fields do have a slight change as we go in the x direction, but we're assuming that is essentially 0. And in the same way, we're assuming that in some y direction, that if we choose I hat, here k hat is into the board, and j hat, k hat is in this direction, then we're also assuming that derivative is essentially 0. So the only non-zero derivative we have is on the z component of the magnetic field. And that's our force in this particular direction. There's some I hat, j. This is all, hang on a second, the I hat component, the j hat component, and the k hat component. Now, let's ask ourselves which way this force is pointing. Well, as we move away from the current loop, the magnetic field component is decreasing the further away you get. So we expect that the partial derivative of the z component is less than 0. We've set up our dipole so it's pointing in the z direction. So our force z component, mu z dbz dz, is negative, which means that when you put a dipole in, in this field above the ring, then it will experience a force downwards, and it's attracting the dipole into a greater field strength. Now, we can make a model for this, because remember, a current loop is like a magnet. So we could think of, this is the current loop. We're just approximating this as a magnet. Our dipole itself is another source north-south magnet. And when you put two magnets with opposite poles adjacent, then you expect a force on the upper magnet down. So this equation, in some sense, is explaining why magnets that are oriented with north-south, north-south attract. And if you flip this, the dipole moment would flip, they would repel. So here we have a qualitative explanation of why two magnets attract. The important point here is that B is non-uniform. That is the essential idea, and that's why we see it in the gradient. Remember, when B is uniform, the force on the dipole was 0, and you see it again in the fact that it's the gradient of mu dot B, which we had talked about as equal to minus the gradient of the potential energy associated with the dipole. Suppose we have a magnet, like a north-south magnet, and it's producing a non-uniform magnetic field. We'll just draw some field lines like that. And now let's put a small current loop inside here of radius r. And what we'd like to do is we have a current I, and we like to calculate the force on this current loop. And our claim will be that if we define a symmetry axis here, call it the z-axis in our k direction, that the force on this current loop is going to be, and this current loop, remember, is a little dipole mu equals mu z k hat, where mu z is the current times the area of the dipole. The z component of the force is mu z times the gradient of the magnetic field. Now, how do we derive that? Well, let's blow up our loop for the moment here and call this the radius r. And at a point here on the loop, we have a current I, and our field line B is pointing like that. And we'll write that field. Now here I'm going to use also a r hat, theta hat, and k hat coordinate system. So it has a radial component and a component in the vertical direction. Then we know that the force dF on the current loop here is equal to the current I ds cross the B field. And so what we get is I. Now ds is in the same direction as the current. And in this case, it's our theta hat direction. So we'll write it as r d theta theta hat. And what we get is r d theta theta hat cross br r hat plus bz k hat. And when we calculate this, we have theta hat cross r hat. That's a component in the negative k hat direction. And we have theta hat cross k hat. Remember, we have r hat cross theta hat is k hat. Here we have theta hat cross k hat. And so we have a component bz r hat. Now, what this is showing us is that if we look a little carefully, the force has a negative k hat piece and a positive r hat piece. So there's a little df here. And as you go around the loop, on every side of it, there will be a little df pointing down. And so what we're seeing here is that when you add all these forces together, we'd expect this point, when we integrate over the whole loop, that this piece will integrate to 0. So this becomes 0, and that's the symmetry. The radial pieces cancel, and we're only left with this vertical piece, and that's equal to minus I r 2 pi br is the force on the wire. Now, at this moment, it doesn't quite look like our result here, but qualitatively, let's just check that the force is down. When you look in the z direction for this magnet, in this particular case, dBz dz is negative, and our dipole mu z is positive, and so we'd expect this component to be negative, and we see that agrees with our calculation here. Our next step is to see how we can apply Gauss's law for magnetism to connect these two results. When we looked at a current loop above a magnet, we discovered that the force on this wire loop was pointing downward and given by this result. Now what I'd like to do is apply our idea of conservation of magnetic flux. That for any closed surface, the magnetic flux in will be equal to the magnetic flux out. And in particular, I'd like to apply that to our magnet. So what we'll do is we don't need our current loop here anymore. And what I'm going to do is pick a equivalent of a Gaussian surface for magnetism. So I'm going to pick a little surface like this. And this surface has an area, radius r, and it's a height dz. We can call this actually, we'll call this delta z. And this is the point z, and of course up here is z plus delta z. Now, on this surface, notice that we have magnetic flux coming into the bottom face. We have magnetic flux coming out of the top face, and there's also magnetic flux coming through the sides. So this little cylinder has 3 different faces, and when we add up the flux, if delta z is very small, then on the side faces we have the radial component of the magnetic field times the area of the side face, and the area of that is 2 pi r delta z. Up here, we have flux coming out. Now, I'm going to write that as b, the z component, which is perpendicular. But remember, this is at the point z plus delta z. And that's times the area pi r squared. And here, I have flux coming in. And so that's minus b of z. But this is only at the point z times the area pi r squared. And all of that is 0. Now, I can write that as b of z plus delta z minus b of z, that's these two pieces. I'm going to bring this term to the other side. So that's minus br. I have 2 pi r. I'm going to divide by the pi r squared. And this delta z, I'm going to divide on that side. So this is rewriting the conservation of magnetic flux. And now you can see that in the limit, as delta z approaches 0, that this is just the partial derivative of z with respect to z. And that's equal to minus, let's write, let's bring the r upstairs and the 2 downstairs. And that's what is equal to minus br. And that is the condition of conservation of magnetic flux. And now let's apply that to our force. So we have minus I r 2 pi. Now we relate. It becomes a plus because of that minus sign. R over 2 dB dz k hat. And we can write that as r pi r squared times bz dz k hat. And you'll recognize this first piece as the magnetic moment. The second piece is that derivative k hat. And that's the force along this axis. And that's exactly what we claimed when we said that the z component of the force on a dipole in a magnetic field is equal to the z component of the dipole moment times the gradient of the magnetic field. This is a beautiful application of Gauss's law for magnetism.